So now, this is question 8, and here we again have sort of the same coefficients here. But an integrator is missing because we are looking at a state space question here. So the first step is to acquire basically the state space model, and then the second part will be to design a state feedback controller that assigns the poles at 3.5 plus minus j. Yeah, so we will first acquire the state space model, and then we will design a state feedback controller that assigns these poles for the closed loop. So, now, as usual, if we are converting a transfer function into a state space model, the most important part is the dynamic part. So, our state space model will be ax plus bu, and we will have the static relation cx plus du. But I know that since I have x dot equals ax plus bu, if I use the Laplace transform, and since I have a transfer function, my initial conditions are 0, so x0 is basically 0. And if I use the Laplace transform here, I'll see that f times x is equal to ax plus a bu. And in order to be able to multiply that, I know that this is not a scalar here, because I have x, this is n by 1, and s is a scalar, so 1 by 1 cannot be multiplied with n by 1. So there is a n by n identity matrix here. So therefore, I know that si minus a times x equals du. Therefore, if I take the inverse, the xu relation here is basically si minus a inverse times b. So this shows me something. It is important to first focus on this here, because this will end up in, if I take the inverse of si minus a, it will have somewhere the minors, the co-minors, you will have somewhere the determinant of si minus a. And this is the important part, because this is the characteristic polynomial. If I want to look for PCS, as I'm used to in the classical control, I can use the determinant si minus a. So therefore, I will start with only this characteristic polynomial, or the denominator of the actual transfer function, in order to come up with the A and B matrices. So the denominator here is for this, or even this equation here. So A and B will determine this. So let's start with that. So I'm basically assuming that this should be s squared plus 7s plus 6. Why? Because I want to determine what A is. And it's only relating to the denominator, so therefore I'm using this relation here. And then I can work out what the actual output relation is, because if we have, since I have x dot equals ax plus bu, if I have x dot here, I'll have an integrator. This will give me x, and then I will multiply that with a. That will give me this ax here, this is a times x. And then I will have also an input, but there's this B matrix. So this is basically the structure that I'm trying to build here. X dot, a times x plus bu gives me this x dot, and the integral of x dot gives me x. So I have the input, but I don't really have the output here. And therefore I will use this here. Since I have this x vector, I can combine it with c here. So take c times that will give me cx. Since I have u, I can multiply that with d and add it to the output. That gives me y. But my whole transfer function here yes, it is the relation between the input and output. But I'm using the state space model in order to generate internal signals like x, state space variables, in order to model it in more detail. So I have access to its internals. Now this first equation here is just about this part here, this dynamic part. Once I have that, I've generated from input the state itself, then I can work out what the output relation should be, because it uses the linear combination of the x's here and the input in order to generate my output vector. Therefore, I have this model Cx plus du that gives me output. But the dynamic part here is here. I have n integrators, because this is n by 1 and each of them needs an integrator. So therefore, I'm modeling from input to the state, not further. And it's quite obvious to work out the differential equation or the Laplace version of this dynamic model. Namely, I cross multiply everything. So I get s squared x plus s 7s x plus 6x should be equal to u. Now, take the inverse Laplace transform of this equation, you'll end up in x double dot plus 7x dot plus 6x equals u. So now, I start by defining my first state space variable, which is basically x itself. Now, if I take the derivative, x1 dot would be equal to x dot. But I want to define a new variable for this in order to prevent high order differential equations, because I just want to stick with the first order, but n times that. So I will say n equations with only first order derivatives. So therefore I need the x2 derivative here, which is basically equal to x double dot. And I can stop here because my highest term here is this. So therefore, this equation here, maybe we can remove this part here, becomes the following. Since I have x double dot, instead of that I can write down x2 dot, and then plus 7, well x dot is basically x2. You can maybe write down x1 dot, but I just want to have one derivative because at the end of the day I have x dot equals something, so there should be only one derivative present. So x2. x2. And then we have 6 times x, but we started with that was x1. So x1 equals u. Of course, I can work it out. x2 dot is now minus 6x1 minus 7x2 plus u. So this is the important relation that I want to work on. Because this has the structure, almost the structure that I need. And I also have this x1 dot equals x2. I can use these two equations in order to define this second order differential equation. And it will look like this. x1 dot is x2. x2 dot is equal to minus 6x1 minus 7x2 plus 2. And if I'm going to use a structure, I can use it. So let's have a summation point. x1 derivative, take the integral, that will give me x1. Now, I also need x2 derivative. If I take the integral, I'll get x2. Now, if I take just one x2, add it here, you'll see that this is basically the first equation. x1 dot equal to x2, and that's it. x2 dot, however, has a little bit more to itself. So let's use this. I need 6 of this, so minus 6. Maybe somewhere here. Okay, minus 6 And I need minus 7 of this, of itself. So my drawing is not really the best, but you get the idea. And then we have in. Since there is 1, I'm not going to put the 1 there, but you can see what I'm trying to get here. Now, what about the output? Here we have the relation between x and u. We know that this is basically 1 divided by s squared plus 7s plus 6. The only thing that is left is the 6 coefficient here. So y divided by u is actually 6 times this. So 6 times x divided by u. You can basically see that y divided by u is 6x divided by u. So cancel these out, you have 6x. But we know that x is equal to x1. So this is not 6x, this is 6 times x1. In a more general form, I can write it down like 6x1 plus 0x2 plus 0u, or 6, 0x plus 0u, which gives me the C matrix, D matrix, and that's it. For this drawing here, I can do the following. I know that 6 times x1, so this times 6, gives me basically the output. This is the input, this is the output, and I have x1 and x2 as internal signals, and I've modeled my transfer function using x1 and x2. So, of course I didn't write down what A and B looks like, so let me get rid of this part here quickly. So the A matrix here is 0, 1, because 0 times x1 plus 1 times x2 plus 0 times u is the first equation here. So the first row is the first equation. Now for the second row, I have minus 6x1, the first one is x1, so minus 6. And minus 7 is the second one, and 1 is this one. Of course, x in this case is defined as x1 and x2. So, yeah, I've written a lot of stuff, but let me recap. Well, we have this relation here, 6 divided by s squared plus 7s plus 6. But we only care about the characteristic polynomial, or the denominator. That will be the state to input relation. And we cross multiply them, obtain the corresponding differential equation, the higher order one, and then introduce new variables at each derivative in order to reduce the overall order. But therefore, we need to use multiple equations in order to meet the requirement, or meet the same differential equation. I need to be able to obtain the same differential equation from this set of equations. That's the important part. And therefore, I have basically a second order path here, but I'm using first order parts in order to achieve that. So the derivative of the derivative of the derivative gives me the higher order derivative that I'm after. But what I'm really doing here is that I'm calling this x2, I'm calling another derivative another name. So it seems like it is a low order differential equation, whereas I have multiple of them, therefore I have the same high order differential equation. So it's the same model, but once I have worked out what the state equations are, I have basically obtained A and B. Once I've done that, I can generate multiple versions of outputs. But since I have a specific one, I'm trying to match that by just adding the 6 here as an equation, and I see that this is 6x or 6x1 in other words, so 6, 0, 0. Now, in case of something like this, if it's 6s plus 7, the only thing that will change is basically this part here. The relation would be 6s plus 7 times x, which will then give me 6 times x derivative. So let me write it down like this. So 6x dot and 7x. But I know that x dot is basically, where is it? It's x2. So this would be x2. This is x1. So therefore, this term will become 7, this will become 6, and again you have the output here. In case of s squared, if you have something like this, or if we write here, s squared or 2s squared plus 6s plus 7, then you have to transform your transfer function into plus 6 as plus b. Why did I write down 2? Because if you divide this, you will see that there's 2 times this polynomial. You have to maybe carry out the polynomial division. You'll see that there is this 2 term here, and then there's the remainder part, the remainder being as plus b. So you have to divide the polynomials, or put it in this form. And if you want to carry on here, you can just do 2s squared plus 14s plus 12 plus as plus b should be equal to 2s squared plus 6s plus 7. So you can see that these cancel out, and basically a should be, I guess, 8, if I'm not wrong. And since that's 7, we have 12, this should be minus 5. And that's basically it. You have a and b, and you can also see that this would be 8, this would be minus 5, and then you will have d equals 2. So the only difference would be to have d equals 2. This is the direct coupling term, and the direct division makes sense since this is the path from input to output on its own, without any state variable. So there's this 2 with states between the output and input. So therefore that term is equal to d. So therefore it's 2. And it was minus 5, so this would be minus 5. And this would be, what was it in 8? So once we have a certain model, how can we return to the transfer function in order to check if we are correct, if we did everything as it should be? So it's quite easy because we will again use this portion here. It's already prepared. We have x-u relation, si minus a, the inverse of that times b. The only thing left is to pre-multiply it with phi, because then we will get cx divided by u. And if I add d, I'll get basically the transfer function. So c times si minus a inverse times b plus d should give us the same transfer function. So once you are done with the conversion from transfer function to state space, what you can do is you can just take a, b, c, and d and plug it into this and see if it's working or not. Of course, this would be time consuming for an exam, so it's way better to just be careful with these steps and be sure that it is correct. Otherwise, you have to take the inverse of a 2x2 matrix if it's a 2x2 system, and that would be time consuming. So now, we know that, let me write down the actual A and B matrices here. We know that A is 0, 1, minus 6, minus 7. B is 0, 1. C is 1, 0. And P was bad, it was 6, 0. That. So we didn't have this part here. I've just had them. So it was just this here. So I can get rid of all the stuff here. So we have obtained the state space model. Now let's try to design a state feedback controller. So, now in order to design a state feedback controller, we have certain poles. Sometimes you may not have them and maybe you're given a setting time overshoot. Again, you have to take the approach of the design polynomial PDS. Use the family again to come up with two poles, or this is the case for a certain setting time overshoot combination, or all that time domain specification data. But if that's not the case, it might be the case that you're choosing just randomly some poles, and I will do that for the observer design that you'll see in the next question. So in this case, we have already the poles, and this is basically PDS, the design polynomial, S plus 3.5 plus J, and then S plus 3.5 minus J. Or in other words, that would be, so we have to multiply them, let me look it up. This is not the wrong, it's the wrong one.
So do we have it somewhere here?
7S plus 13.25. Yeah. Now, this is PDS, and I've written this for a reason. It's not random, because for designing a safety pack controller, we need to evaluate the Ackermann formula, which uses basically a vector, 0, 1, since this is a 2x2 system, the control matrix inverse, and a certain PDS S equals A. So therefore, first we need to evaluate what PDA is. That would be the square of A. Now, since this is A, minus 6 and minus 7, and 7S. So basically, seven times 0, 1, minus 6, minus 7, plus 13.25, 0, 0, 13.25. So first of all, you have to do is matrix multiplication. You take the square, 7 times that, and then the identity matrix, because I'm plugging a matrix, size should be compatible. And then you should evaluate PDA. So that's one hell of a job. And once we've done that, this is again time consuming, by the way. Once we have that, luckily we get this here, which is not always the case. We don't really have always a structure like this, but it pops out like this. And then we need phi c, controllability matrix, which is B and A times 3. Therefore, we have 0, 1, 0, 1, and the remainder part seems to be 1 minus 7. It basically shows the second column here, because 1, 0, 0, 1, so 0 times this column, 1 times this, added up gives us this here. So first of all, this should have an inverse. So if the rank of this is 1, if the determinant is 0, you can't take the inverse. Therefore, you will not be able to assign the poles as you wish. But since here we don't have that, the inverse of this, did I write it down, is, since it's a special one, we have 0, 1, 1, 0, 7, 1, 0. Now we have phi c, PDA, and then the 0, 1 vector. Therefore, we can calculate what k looks like. So 0, 1, 7, 1, 1, 0, and 7.25, 0, 0, 7.25. That gives us k equals 7.25 and 0. So now using this, what we're basically doing is we have basically a safety feedback law, and in this case we have a negative sign, a minus bk. And actually, just for this case, we have a special case here. It corresponds to 725x1, if you look closely. Which means that we take basically x1, which is in this case something like this, multiply it with k, and apply it to the input. Now, of course, you can maybe use a certain, let's say, input here, r, then this would be plus r. This would correspond to a certain input r. So this is basically what we do. We again have a state, and we have a feedback structure, but it looks different because most of the time we take the output for classical control, we take the reference, feed that information back. But here we use the states to feed it back, to change the system behavior, to have the closed loop pulse like this, and it's quite different than using a p-type controller. But for this special case again, I know that we have a relation y equals 6 times x1, and you can see basically that u is somewhat similar, something like this. Well, if I'm fancy, what I can do is I can just add 7.25 divided by 6 times r as a feedback law in order to end up in 7.25 divided by 6r, and you can immediately see that r minus y pops up. 7.25 divided by 6e would be then the feedback law. This would correspond to a p-type control. It doesn't have to be. It was a special case. The pole assignment that was chosen here is basically on the root locus, and you can verify that. You can see that this is indeed the case. I'm out of place. So you can see that this is 7. So we have minus 1, minus 6. They meet here. One goes up, one goes down. And this coordinate here is minus 7 divided by 2, minus 3.5. So therefore, this is I, this is minus I. Your point is on the root locus here. Therefore, the controller, the state feedback controller, is actually a p-type controller, the equivalent of that. But it doesn't have to be, because if you state feedback, you can also assign this set of poles, which is not on the root locus, which is not going to be a p-type controller, and which will have definitely a different structure. It will use x2. And you can just try it out. You can just change the poles here, repeat the whole process, and you will see that it will not be corresponding to a p-type controller. But in that case, again, it's a special controller. If you have, let's have minus k1, x1, minus k2, x2, and then a certain reference and a coefficient for that. Well, I know that x1 is basically x, but x2 is x1 dot plus br. So we have a derivative feedback, a proportional feedback. It would correspond to kp and kd. So it's kind of a PD feedback if it's a 2x2 system. That would correspond to a PD feedback. So what you can do is you can just use GX and PD back here. Of course, this would not track. Therefore, I have V times R, something like this. So R times V, you have an amplification. But it's not the best control strategy, because if you have a certain output disturbance, input disturbance, you would not track the output. It's a semi-closed loop approach because you're just changing the pole locations. But this part is an open loop sort of control or compensation. Therefore, it's not the best, but you get the idea. The pole assignment corresponds to a feedback PD control for a 2x2 system if you have K1 and K2. If you are on the root locus for p-type controller, your state feedback will be a p-type controller. So that's basically it. And this was question 8.